introduce myself? Yes, hello children, this is Karthik, Senior Physics Faculty from Perfect Academy, and in this session we are going to understand the next topic, and which is followed by magnetic effects of current, that is magnetism. In this topic we are going to understand, in this session we are going to understand all these 5 things, that is magnet, what is the meaning of magnet and their properties, and various terms related to bar magnet, the combination of magnets, and last 2 are magnetic field strength and the field lines, the properties. Let us start now. Let us know what is the meaning of magnet. What do you mean by magnet? The magnet is nothing but the substance which can attract the magnetic materials like iron, cobalt, nickel. So it will have a properties like attractive property and directive property. What are the main properties of magnet? Main properties of magnets are, one is attractive property. Just now I told you the meaning, attractive property. What is the meaning of attractive property? If the magnetic substance is nearby any other magnetic material, so it could able to attract towards themselves, and that property is called as an attractive property. And the next one is what? Directive property. What is the meaning of directive property? If any bar magnet is suspended freely, so let us suppose this is a one bar magnet that I suspended freely with the help of one small rope, then what will happen? It will try to come align, rest in towards, in the direction of north and south. So the point, the end which is showing towards the north direction will be called as a north pole. The end which is pointing towards the south direction will be called as a south pole. So every bar magnet will have a 2 poles, north pole and south pole, and no magnet will be available with a single pole. That means unipole magnets do not available in this universe. Always the magnets will have a 2 poles. Even if you break this magnet, if you consider this as a one bar magnet which is with the north pole and south pole, even if you break into small parts, even for those small parts also they will again have a north pole and south pole. So unipoles do not exist. The bar magnet will always have a 2 poles, north pole and south pole. And now let us understand very important terms that are related with the bar magnet. One is that important terms. Let us know what are they. One is called magnetic length. What is the meaning of this magnetic length? Let us understand. So let us suppose this is a one bar magnet and it is having a length L, and it will have definitely 2 poles. What are they? South pole and north pole. Now this L will be called as a geometrical length of a bar magnet. Geometrical length in the sense the actual length of a bar magnet, and this bar magnet is having a 2 poles, south pole and north pole. So if I think this is a one point where the south pole is concentrated, and here is the one point where the north pole is concentrated, then the distance between the south pole to north pole inside the bar magnet, the distance between the center of south pole to center of north pole will be called as a magnetic length. Conventionally it is represented as a 2L. It doesn't mean that it's a double of the length. No. Conventionally, if L is a geometrical length, the magnetic length is denoted by the 2L, and its unit is nothing but meters. It's a magnetic length, so its unit is nothing but meters. And now the next one is magnetic pole strength. Magnetic pole strength. What is the meaning of magnetic pole strength? It is denoted by the letter small m. So what is the meaning of magnetic pole strength? The ability of bar magnet to attract or repel another pole. So for example, this is a one bar magnet and here I have another bar magnet which brought nearby each other. Then if the like poles are facing each other, it will experience the repulsion. If unlike poles are facing each other, it will experience the attraction force. Then the magnitude of the force, how much extent it is experiencing the force, that will be given by the term called magnetic pole strength. So you don't have any formula, but it has a one unit called ampere into meter. The unit of a magnetic pole strength is ampere into meter. And further, this magnetic pole strength is denoted by, it is depend upon the area of cross section. the magnetic pole strength depend upon area of cross section. This is very very important point. So we understood what is the meaning of magnetic length, what is the meaning of magnetic pole strength. And here let me tell you one more point. If L is nothing but geometric length and 2L is nothing but magnetic length, conventionally it is represented as a magnetic length. Actually the magnetic length is equals to 5 by 6 times of geometrical length. This is a relationship between magnetic length and geometrical length. So if magnetic length is denoted as a 2L, let me call magnetic length as a LM. Now this will be equals to what? 5 by 6 times of actual length. Actual length is nothing but L I told. So 5 by 6 times of the actual length. For practical purposes and all, we will generally consider the magnetic length and the geometric length are almost equal to each other. For all our problems and the practical purposes, we will treat the magnetic length and the normal length, I mean geometrical length, or both are equal to each other. So here you understood about the magnetic length, which is denoted by conventionally 2L, and it is measured with the unit called meter. And what is the meaning of magnetic pole strength? The ability of a bar magnet to attract or repel another magnet, and it is measured with the unit called ampere into meter, and it depends upon area of cross section. It is denoted by the letter small m. Now let us know another very 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 important term that is related to bar magnets, that is magnetic moment. Here it is the very very important one, magnetic moment. What is the meaning of magnetic moment? You all might have heard about the electric dipole moment. What is the meaning of electric dipole? Two equal charges having opposite nature separated by certain distance, that constitutes the electric dipole. And what is the meaning of electric dipole moment? That is nothing but either of the charges multiplied by the distance between them. The product of either of the charges multiplied by the distance between them, that will be called as an electric dipole moment. In the same way, so every bar magnet will have a two poles. What are they? South pole and north pole. So the constitution, I mean the arrangement where the two poles are have some gap between them, that will be called as a magnetic dipole. So just like electric dipole is having a electric dipole moment, the magnetic dipole will also have magnetic dipole moment, which will be simply termed as a magnetic moment. So the magnetic moment is nothing but, so since in every bar magnet I will have a south pole and north pole separated by the distance called magnetic length, separated by the distance called magnetic length, so therefore they will have a certain magnetic dipole moment, and that is what called magnetic moment, denoted by the letter capital M, and it is denoted as a, it is defined as a the product of pole strength and magnetic length, the product of pole strength and magnetic length. And just like electric dipole moment is in vector quantity, the magnetic moment is also vector quantity, and whose direction will be from south pole to north pole. So for this bar magnet, the magnetic moment is from south pole to north pole, and its product, I mean its value is nothing but m into 2L. And what will be its units? Its units are nothing but the pole strength is measured with the unit called ampere into meter, the magnetic length is measured with the unit called meter, therefore ampere into meter square. Ampere into meter square. This magnetic moment is depend upon two factors. What are they? One is pole strength, another one is the magnetic length. Now let us try to understand what will be happen if the bar magnet is cut into n number of pieces. So far we understood about the few important terminology related with the bar magnet. We understood about magnetic pole strength, we understood about magnetic length, and finally we got to know what is the magnetic moment. Here is the definition for magnetic moment, right? So now let us look into this. There is a one bar magnet and having the magnetic moment M, and it is divided into n parts, n equal parts. They are nothing but n equal parts, and that made along the length. Along the length in the sense like this. They are divided into n parts along the length like this. Then what will be the magnetic moment for each piece? So let me call the magnetic moment for each piece is m prime. Now here what will be happen? The length is remaining same, therefore there will be no change in the magnetic length. Then what will be happen for pole strength? Since it is divided along the length, the area of cross section will be also decreases by n times. Therefore, what I can say, the pole strength is also decreases by n times. Since the pole strength is depend upon area of cross section, and here I have divided into n pieces here, n number of equal pieces here. Therefore, what I can write, the pole strength is divided by n. Therefore, here what I can say, m divided by small n. Therefore, whenever the bar magnet is cut into n equal parts, then for each part, what is the magnetic moment? That is given by m by n. Then immediately one more question will be arises. What is that? If I have the same bar magnet which is having south pole north pole with a magnetic moment m, if I break into n parts perpendicular to its length, then what will be magnetic moment of each part? So let us suppose it is again break into n number of equal parts. Just like here I have done, here also n number of equal parts I have divided. Then here what is not changing? What is changing? The magnetic pole strength do not changes because the area of cross section is not affected by this cutting. Which is changing? The magnetic length is changing because the total length is divided into n number of equal parts. Therefore, what is going to be the new magnetic moment? Shall I note down here? The new magnetic moment, shall I call it as an m prime? Then that is going to be equals to pole strength do not changes. But magnetic length will be divided into n parts. Therefore, what I can write? 2L divided by n. So again, I have the same formula. What is that? M by n. Therefore, from these two, what you understood? When the bar magnets are break into n equal parts along the length or perpendicular to length, the magnetic moment for individual species is nothing but m by n. It is nothing but m by n. This is an important thing that we have to understand. Now, let us know about what will be happen when the two bar magnets are aligned at different angles. I mean, what will be the resultant magnetic moment when the two bar magnets are aligned at some angle. Let us look into this situation. Shall I clean up this? Here we need to understand the combination of bar magnets. What here we are interested to study? We are interested to study that magnets. Here we are interested to study about what will be the resultant magnetic moment when the two bar magnets are aligned at some angle with each other. So let us suppose I have the two important situations here. One is that like this. There is a one bar magnet having the south pole and north pole. Let me call it is a first magnet. Therefore, S1, N1 I would like to call them. Then M1 is going to be the magnetic moment. And there is another magnet which is arranged like this, and let me call its south pole is and its north pole is like this, and it has a magnetic moment m2. Then what will be the angle between the axes of the two? Let me call it as an theta. Then what is going to be the net magnetic moment? The net magnetic moment is nothing but, since the magnetic moments are nothing but two vector quantities, and when the two vectors having some angle theta between them, the resultant vector magnitude is nothing but under root a square plus b square plus 2ab cos theta. The same thing we could apply here. M1 is a vector a and M2 is nothing but vector b having the some angle theta between them. Then M net is nothing but what? Resultant vector magnitude, that is net magnetic moment magnitude. The net magnetic moment magnitude I am writing, and this could be written as under root m1 square plus m2 square plus 2m1 m2 cos theta. This is the one case. Now let us look into this situation. Here I have the same S1 N1 which is having the magnetic moment m1, and here I have another bar magnet which is having north pole and south pole like this. It is second magnet, right? So S2 N2. Then what is going to be the resultant magnetic moment? Let us suppose here also the angle between the two axes is nothing but theta. Then what is the resultant magnetic moment? Here you have to see the difference between these two things. What is that? Here S2 N2, S1 N1 both are aligned in the same direction. I mean they have the same starting point. That's why A and B, two vectors I consider, and angle between them is theta. That alone I have done here. And what about here? They don't have the same origin. This can be imagined like this. This is the magnetic moment M1 and this is the magnetic moment M2. And here I mentioned theta, that is nothing but this one. This is nothing but theta. Now, what is the angle between these two? Actually, that is nothing but 180 minus theta. Got my point? So the difference between here and here is nothing but here they have the same origin. Always the two angle between the two vectors has to be mentioned if they have the same origin. So these two have been originated from this point. Therefore, I have directly written the formula. And what about here? One is like this and another one is like this. They don't have the same origin. So here I try to get the same origin so that I have the angle between the two magnetic moments as a 180 minus theta. Now let me substitute back to the same formula what I know already. What is going to be the net magnetic moment in this case? That is going to be under root same formula m1 square plus m2 square plus 2m1 m2. Instead of theta here I have 180 minus theta. Therefore this formula is going to becomes minus 2m1 m2 cos theta. This is going to be the net magnetic moment. Yes. So hope you understood the difference between these two cases. Now let us see some applications of the same concept, that is arrangement, the alignment of bar magnets in different ways. Okay, well, so this is the one thing that we have to understand, and let us see these different situations. Let us see these different situations. Let us try to answer this. So here I have two bar magnets and both have the same magnetic moment, but one kept upon another like this. Then what is going to be the resultant magnetic moment? In this case, the resultant magnetic moment magnitude equals to 0. Why? Because the two are opposite to each other. And what about this? If I have one bar magnet with the south pole and north pole and another bar magnet with the south pole and north pole arranged like this, then what is the resultant magnetic moment here? Let me assume the magnetic moment for the both magnets is equal to each other, that is M and M, and they have the 90 degrees angle between them. Then what is going to be the resultant? Just now we have seen what is the formula. M net magnitude is nothing but under root m1 square plus m2 square plus 2m1 m2 cos theta. Here they have the same origin, right? Therefore, what is going to be the net magnitude? The net magnetic moment magnitude is given by under root m square plus m square plus 2m square cos 90, it is 0. Therefore, what will be left out? Root 2 times of m. This is the net magnetic moment for this arrangement. So, these are very simple things, and let us look into this thing now. So, here I would like to take one situation where the magnet, the bar magnet or magnetic needle that has bent into arc shape. Let us suppose there is a one bar magnet. There is a one bar magnet whose length is L. Its magnetic length is 2L. It has a south and north pole with a magnetic moment M such that M into 2L. This is a one bar magnet, or let me assume it is a one magnetic needle. Now the same magnetic needle is bent into arc shape such that at the center, the either ends of the magnetic needle are subtending an angle of theta at the center. And let us suppose R is the radius. R is the radius of full circle that could be formed by this arc. Okay, now from this information we need to calculate what is the magnetic moment. So here it is M. Here it will not be equals to the same amount. Why? Because the pole strength of course do not changes, but the net magnetic length will be changes for this case. Got my point? Since the area of cross section is not affected after bending, what would happen? The pole strength will not be affected, but the magnetic length will be changes. Here we have to calculate what is the new magnetic length. Let us try to attempt it. So this is going to be what? The distance between south pole and north pole. Am I right? So let us solve. This is south pole, it's a north pole. So the new distance between the south pole and north pole I have to try to find out. Well, now here it is an R. Now you tell me this one. If I draw one normal to this line is dividing this total angle into theta by 2 and theta by 2 respectively. The total angle of subtending is how much? Theta. Then if I draw this normal line, this equally splitting the angle into two parts, theta by 2 and theta by 2. Then what is going to be this amount now? Or cos theta by 2 or sin theta by 2. Therefore, this amount is how much? Or sin theta by 2. As well as this, what about this amount? Or sin theta by 2. What is the total distance? 2 or sin theta by 2. This is going to be the actual length between South Pole and North Pole. Right? Now see this one. If L is the length of a bar magnet and 2L is considered as a magnetic length and magnetic moment will be defined as a M into 2L. The same procedure let me follow here. Here the distance between south to north is how much? 2 r sin theta by 2. What is the pole strength? M. Then what could be the magnetic moment? Shall I call the new magnetic moment as an M prime? Okay. Then that M prime will be nothing but what? The pole strength multiplied by 2 times of L. 2 times of here, if L is the length, I have written as a 2L. If this is the distance like 2 r sin theta by 2, while defining the magnetic moment, I have to multiply with the 2. Therefore, what will be happen? 2 times of 2 r sin theta by 2 multiplied by M will gives you the new magnetic moment. Now, it's all about rearranging this expression. With that, we will conclude one important expression. Let us proceed here. Now, here the same length of magnet that's been bent into here. Correct or not? Then what is the arc length? Arc length is nothing but what? Arc length. Usually arc length is nothing but r into theta. Here r is nothing but radius. Therefore r. What is the angle? That is theta. That will be the same. This arc length is nothing but equal to length. Therefore what I can write? L equals to r into theta. From here what is an r? L divided by theta. Shall I substitute back to my expression? Then what I'm going to get? Shall I rearrange this expression like this? 2 times of M into 2 into L by theta sin theta by 2. The same expression, just rearranging like this. 1, 2 I have taken out. M into, in the place of R, I take in the L by theta and the 2 is remaining same here. And here the 10 sin theta by 2 is left over. Then what I could write here? 2 times of M into 2L divided by theta sin of theta by 2. Therefore, what I can conclude here? I can conclude here like 2m by theta times of sin of theta by 2. This is the new magnetic moment of this arc. Okay, so if L is the length of a bar magnet, if small m is the magnetic pole strength, the magnetic moment is defined as a m into 2L. If the same bar magnet, or let us suppose it is a magnetic needle, if the magnetic needle is bent such that if it subtends angle theta at the center, then the new magnetic moment is given by the expression 2m by theta times of sin of theta by 2. This is going to be the expression. Now let us make some important conclusions from this expression alone. Well, so let us assume I have like this. There is a one magnetic needle which is bent like this. Therefore, what could be this angle now? 90 degrees only, right? So, what is the angle subtended by this magnetic needle at the center now? 90 degrees, which is equals to pi by 2 radians. Done. Then what is going to be the new magnetic moment now? The new magnetic moment that will be equals to what? 2m divided by what is the theta? Pi by 2 radians multiplied by sin of theta by 2. Theta by 2 is how much? Pi by 4. And finally what we will get? 4m divided by pi into 1 by root 2. And this is what we can write? 2 into 2. So 2 root 2 m divided by the pi. This is going to be the new magnetic moment for this arrangement. Well, in the same way, if it is like a semicircle, if it is like this, let us suppose the bar magnet or magnetic needle is bent into semicircle with the radius of r. Then what is its magnetic moment? Again here what is the theta subtended by 8? Pi radians. Shall we substitute back? Then what will get? M prime equals to 2m by pi times of sin 90 equals to 1. So therefore this is going to be the new magnetic moment for this arrangement or for this configuration. So when our bar magnet having the magnetic moment m is configured in a way such a way that it is subtending an angle of theta, then the magnetic moment equals to 2m by theta of sin theta by 2, and here we have seen the two application. In the next section we are going to deal with what is the magnetic field and its strength, and what are the properties of field lines, and the next things we will see. Thank you.